On December 7, 1944, 4 days after a Japanese fighter pilot rammed an American bomber out of the sky over Tokyo, a truck arrived at the gates of the Tachikawa Army Aviation Technical Research Institute carrying what was left of the aircraft. The men waiting for it were not soldiers. They were engineers, metallurgists, electrical specialists, instrument technicians, the best Japan's aviation industry had. Their job was simple: take the wreckage apart, examine every component, write a report on what they found. They had done this before. In 1942, Japanese engineers had examined captured B-29 flying fortresses, intact ones, flown to Japanese airfields by their own test pilots. The B-29 had impressed them, but the B-29 was a machine they understood. It was bigger than anything Japan built, heavier, tougher, but it belonged to the same world. The same engineering principles, the same generation of technology. What arrived at Tachikawa that December morning did not belong to the same world. The wreckage was mangled. The fuselage had broken apart on impact, wings sheared off, engines buried in mud. But the engineers were not looking at the shape of the aircraft. They were looking at what it was made of, and how. Here is the detail that matters, and I want you to hold on to it, because everything in this story comes back to it. The first thing they pulled from the wreckage was a section of aluminum skin, standard aircraft aluminum, or so it should have been. But when they measured it, the thickness was not a round metric number. It was an imperial measurement, 1/16 of an inch, and the alloy was not one they recognized. If you enjoy videos like this one, a like and a subscribe help these stories reach the people who care about them. That aluminum panel was the first sentence of a very long message, because the men at Tachikawa were about to discover that almost nothing inside this aircraft could be reproduced by Japanese industry. Not the metal, not the wiring, not the glass, and especially not the 5 identical devices bolted behind the gun turrets, devices that contained a technology Japan had never seen in any aircraft, from any country, in any war. The bomber was a B-29 Superfortress. By the time the engineers finished their examination, the word they kept returning to was not impressive. It was not advanced. According to post-war interrogations, the reaction that spread through Japan's aviation establishment was closer to disbelief. The quiet, professional disbelief of men who understood exactly what they were looking at and exactly what it meant. But to understand why a piece of aluminum and a 50-pound metal box broke something inside Japan's best engineers, you need to understand what Japan believed about itself in 1944. Because the story of what they found in that wreckage is not a story about an airplane. It is a story about the moment a nation's engineers looked into a machine and saw the future, and understood they were not in it. In the autumn of 1944, Japan was losing. The men in Tokyo knew this, but losing and being finished are not the same thing. Japan had lost Saipan in July. It had lost the Philippine Sea. The Americans were closer than they had ever been, but Japan still controlled its home islands, still had factories producing aircraft, still had 6 million men under arms. The plan, the only plan left, was to make the cost of invasion so catastrophic that America would negotiate. That plan depended on one assumption: that the technological gap between Japan and America was manageable, that Japanese engineering, Japanese ingenuity, Japanese willpower could offset American production, that the enemy built more, but Japan built well enough. The wreckage sitting in the hangars at Tachikawa was about to destroy that assumption, not with a single revelation, but with a cascade of them, each one worse than the last, each one deeper, each one quieter. And the first one started with a question so simple that it should not have mattered at all. The question was about a rivet. When the engineers at Tachikawa pulled aluminum panels from the B-29 wreckage, they expected to find rivets similar to their own, functional, adequate, slightly irregular in spacing because every aircraft panel in Japan was fitted by hand, by a craftsman who eyeballed the gap and drilled where his experience told him to drill. Japanese aircraft were built by men who had spent years learning their trade. Each fuselage was, in a small way, unique. That was the system. It worked. The rivets on the B-29 panel were not like that. They were identical, every single one. The spacing between them did not vary by a millimeter. The countersinking, the depth to which each rivet head sat flush with the skin, was uniform to a degree that the Tachikawa engineers could measure, but could not explain through hand labor. These rivets had not been placed by a craftsman making judgments. They had been placed by a process a system so precise that the human hand was no longer the limiting factor. That distinction matters more than it sounds. Remember it, because in 1944, Mitsubishi's Nagoya complex employed 43,000 workers. It was Japan's largest aircraft facility. And in all of 1943, those 43,000 workers had produced 1,029 Zero fighters, fewer than 3 per day. Each one was built substantially by hand. When a finished Zero needed to reach the flight test airfield at Kagamigahara, there were no paved roads wide enough for a truck to carry it. Mitsubishi engineers solved this problem by hitching the aircraft to a team of 20 oxen. When the oxen began to die from exhaustion and malnutrition, they switched to Percheron draft horses. The Americans, meanwhile, were building B-29s, aircraft so complex that each one contained 10 miles of electrical wiring, over 40,000 separate parts, and a pressurized cabin that required seals Japan had never manufactured, at a rate that would have sounded like propaganda to any engineer at Tachikawa had they known the actual numbers. They did not know, not yet. The rivets were the first clue. The second clue was the aluminum itself. Japanese metallurgists cut samples from the B-29 skin and tested the alloy composition. What they found was an aluminum alloy with properties they could identify but could not replicate, not because they didn't understand the chemistry, but because the raw materials required to produce it were no longer available to Japan. Bauxite shipments from Malaya and the Dutch East Indies had been cut by American submarines. By late 1944, Japan's aluminum production was collapsing. It would fall to 9% of its peak by the following summer. The B-29's skin was made of a material that Japan was physically running out of. But here is what made the aluminum finding devastating, rather than merely disappointing. The engineers recognized that the alloy was not special. It was not some secret formula. It was standard American aircraft-grade aluminum, the same material Boeing used on everything from its commercial airliners to its smaller bombers. The Americans were not using a rare alloy to build the B-29. They were using an ordinary alloy in extraordinary quantities, with extraordinary consistency. That was worse. A secret formula can be stolen. An industrial base cannot. Now, I said the engineers pulled something else from the wreckage, the 50-pound metal boxes bolted behind the turret positions. There were several of them, damaged but partially intact. When the electrical specialists opened the casings, 3/8 of an inch of solid steel, what they found inside was the thing that changed the conversation at Tachikawa from admiration to something else entirely. Inside each box was an analog computer, not a mechanical calculator, not a simple linkage of gears. An electromechanical computing device built by General Electric, containing hundreds of relays, resistors, and precision-wound components, designed to do one thing: aim guns at attacking fighters and correct for airspeed, altitude, temperature, humidity, gravity, and the relative velocity of the target, in real time, continuously, automatically. The B-29 carried 5 of them, one for each sighting station. Each computer could control multiple turrets simultaneously. If a gunner was killed, his turrets automatically transferred to another station. The system was interconnected. It was redundant. It thought faster than a human could, and shot more accurately than any gunner in any air force in the world. Japan had nothing like it, not in development, not on a drawing board, not in theory. And the engineers at Tachikawa knew why. Because building one such computer was an achievement. Building 5 identical ones for a single aircraft was impressive. But what they did not yet understand, what would take them weeks to fully grasp, was how many B-29s existed. How many of these computers were already flying over their country, every night, in formations so large that Japanese radar operators had stopped trying to count individual aircraft. That number is the next part of this story. And when the engineers finally learned it, the word they used was not impossible. It was quieter than that. Here is the number. By December 1944, when the Tachikawa engineers were still cataloging parts from a single B-29, the United States Army Air Forces had already accepted over 1,500 Superfortresses from 4 assembly plants spread across the American continent. Boeing's factory in Wichita, Kansas. Boeing's second plant in Renton, Washington. A Bell Aircraft plant in Marietta, Georgia. A Glenn L. Martin plant outside Omaha, Nebraska. 4 factories, running 2 shifts, 9 hours each, 7 days a week. And they were accelerating. By the spring of 1945, while the Tachikawa report was still being circulated among Japan's aviation leadership, The Wichita plant alone was producing 4 completed B-29s every working day, 100 per month from a single facility. All 4 plants combined were delivering 375 Superfortresses per month, each one carrying 5 General Electric fire control computers, 4 Wright R3350 engines with 8 turbochargers, a fully pressurized cabin, and 10 miles of wiring. Think about what that means. Not the number of airplanes, the number of computers. 375 aircraft per month, 5 computers each. That is 1,875 analog computers rolling off assembly lines every 30 days. Devices that Japan's best electrical engineers could not build one of. America was producing them by the thousands and installing them as components, not as marvels, not as prototypes, but as standard equipment, no more remarkable to the assembly workers in Wichita than a seat or a window latch. The engineers at Tachikawa did not learn these exact figures. The full production data was classified, but they did not need exact figures. They had something more revealing. They had the sky over Tokyo. On the night of November 24th, 1944, 9 days before Corporal Nakano rammed the B-29 that ended up at Tachikawa, 111 Superfortresses appeared over the capital. It was the first B-29 raid on Tokyo from the Marianas, 1,500 miles to the south. Japanese radar operators tracked them coming in at altitudes above 25,000 feet, higher than any bomber formation Japan had ever faced. The anti-aircraft guns could not reach them. Most of the interceptors could not reach them either. And this is where the next discovery at Tachikawa connected to everything else. Among the wreckage, the engineers found the pressurization system, or what remained of it. Seals, valves, ducting, regulators. The B-29's cabin was divided into 3 pressurized compartments connected by a tunnel that ran over the bomb bays. The crew breathed filtered, heated, pressurized air at 30,000 feet, the way a man breathes sitting in an office in Nagoya. They wore no oxygen masks. They wore no heavy flight suits. Their hands were not numb. Their minds were not foggy. They could operate complicated equipment, the fire control computers, the radar, the navigation instruments, with full mental clarity at altitudes where Japanese pilots were gasping through rubber masks, fingers too cold to feel the trigger. Japan understood pressurization in theory. It had never built a pressurized combat aircraft that worked. The seals required materials and manufacturing tolerances that Japanese industry could not consistently achieve. Every attempt leaked. The B-29 system did not leak. It maintained cabin pressure equivalent to 8,000 feet, while the aircraft flew at 32,000. The engineers at Tachikawa could see how it was done. They could document every valve. They could not reproduce the seals. But the pressurized cabin was only half the altitude problem. The other half was what made those massive Wright engines perform at the edge of the atmosphere, the turbochargers. Each R3350 engine carried 2 exhaust-driven turbochargers that forced compressed air back into the cylinders at extreme altitude, maintaining sea-level power where the air was too thin for a normal engine to produce more than a fraction of its rated output. The turbocharger is a brutally simple concept. Exhaust gas spins a turbine. The turbine compresses intake air. More power, more altitude. Simple in concept, murderous in execution. Because the turbine blades spin inside a stream of exhaust gas at over 1,000 degrees, and the alloys required to survive that environment for hundreds of hours demand nickel, chromium, cobalt, metals that Japan had been short of since 1942 and was now almost entirely without. Japan had been trying to build reliable aircraft turbochargers since 1937. 7 years. 4 manufacturers, Mitsubishi, Nakajima, Hitachi, Ishikawajima, all failed to produce units that lasted more than a handful of flight hours before the blades cracked, the housings warped, or the butterfly valves exploded. The Americans had solved this problem so thoroughly that they were bolting 8 turbochargers onto every single B-29 that left the factory. 1,500 per month just in turbochargers, as routine as rivets. And now, the cascade was becoming clear. The engineers at Tachikawa were not looking at an airplane. They were looking at an industrial civilization that could produce, in bulk, components that Japan could not produce at all. Not one, not a prototype, not a proof of concept. But Japan tried. Of course Japan tried. And the story of that attempt, what Nakajima Aircraft Company built in a hangar at Koizumi, and what happened to it, is the story of an answer that arrived too late, too few, and too broken to matter. In February 1943, more than a year before the first B-29 ever appeared over Japan, the Imperial Japanese Navy issued an order to Nakajima Aircraft Company. Build a 4-engine long-range bomber, something that could strike distant targets, carry 4,000 kilograms of bombs over 2,000 nautical miles, and fly at 320 knots, something that could match what the Americans were clearly building. The engineers at Nakajima had already tried once. Their first 4-engine bomber, the G5N Shinzan, had been a disaster, overweight, underpowered, so sluggish that the Navy demoted it to a transport. The Shinzan's design had been based partly on a Douglas DC-4E airliner that Japan had purchased from America before the war for $950,000, shipped to Tokyo by sea, and quietly disassembled for study. The results had been humiliating. So when the Navy came back in 1943 and said try again, Nakajima's designers started from scratch. They studied the one American bomber they had examined thoroughly, the captured B-17 Flying Fortress. They borrowed its structural logic. They designed a cleaner airframe, a mid-mounted wing with laminar flow sections, tricycle landing gear. They powered it with 4 Nakajima Homare radial engines producing 2,000 horsepower each, competitive numbers on paper with the B-29's Wright R-3350s. And they added something they knew they needed if the aircraft was ever going to operate at the altitudes where the B-29 lived: Hitachi Type 92 turbochargers. They called it the G8N Renzon, mountain range. The name was aspirational. The aircraft was real. Nakajima completed the first prototype in October 1944, and it flew on the 23rd, 18 months from order to first flight. That is fast. That is genuinely engineering under wartime conditions. And when the G8N lifted off, it performed. Its speed, its ceiling, its range, all fell between the B-17 and the B-29. American evaluators who tested a captured Renzon after the war noted its flight characteristics were respectable. The airframe was sound, but remember the turbochargers. The Hitachi 92 units mounted on the Renzon's engines were the best turbochargers Japan had ever produced. They worked, for a while. Then the blades cracked. The seals failed. The turbine housings warped under heat that the available Japanese alloys could not sustain. The engineers at Nakajima documented minor problems with the turbo superchargers, in the careful language of men who understood that minor problems with turbochargers are not minor problems. A turbocharger that fails at 30,000 feet does not inconvenience the crew. It kills the engine. An engine that dies at altitude on a 4-engine bomber does not slow the aircraft down. It turns a bomber into a mathematics problem. Whether 3 remaining engines can sustain flight at that weight, at that altitude, in combat. The Americans had solved this mathematics by building turbochargers that lasted. Japan was solving it by hoping. And even hope required aluminum. By the spring of 1945, the 2nd, 3rd, and 4th Renzon prototypes were being assembled at Nakajima's Koizumi plant. The 3rd prototype was destroyed on the ground when American carrier aircraft strafed the factory. The others sat in various stages of completion, waiting for parts, waiting for materials, waiting for engines that worked. The Navy had planned for 16 prototypes and 48 production aircraft by September 1945. That plan required aluminum alloy that no longer existed in Japanese supply chains. Submarine warfare had severed the bauxite lifeline from Southeast Asia. The stockpiles were gone. In June 1945, someone at Nakajima proposed a solution so desperate that it tells the entire story in a single sentence. They proposed building the Renzon out of steel, not as an experiment, not as a weight study, as a production aircraft. The G8N3 Renzon Kai Model 23, an all-steel heavy bomber, because Japan no longer had enough aluminum to build airplanes out of aluminum. Picture what that means. Steel is roughly 3 times heavier than aluminum for the same strength. An all-steel Renzon would have been so heavy that it would have needed more powerful engines Japan did not have, to achieve performance that was already inferior to the B-29. It was not a plan, it was an admission. The proposal never went beyond paper. The war ended first. So here is the ledger. By August 1945, Japan had built 4 Renzon bombers, total. In the same period, the United States had built nearly 4,000 B-29s. The ratio is 1 to 1,000. And the 4 Japanese aircraft could not reliably fly at the altitudes their turbochargers were designed for, while every American aircraft carried 8 turbochargers that worked, 5 computers that aimed guns automatically, a pressurized cabin, and enough fuel to fly 3,000 miles and back. But the Renzen was not the real failure. The Renzen was a symptom. The real failure was something the Tachikawa engineers understood before the Navy did, before the Army did, before anyone in the Imperial General Headquarters was willing to say it out loud. The real failure was not that Japan could not build a B-29. It was that Japan could not build what built the B-29. The thing behind the airplane, the thing no wreckage could fully reveal. What was that thing? That is what the engineers tried to explain in their reports. And the answer had nothing to do with airplanes at all. The thing behind the airplane was the system that produced it, not a factory, a system. And the difference between those two words is the difference between what Japan understood and what Japan could not replicate. Japan had factories. Mitsubishi's Nagoya complex covered acres. Nakajima operated multiple plants across the Kanto Plain. Kawasaki, Aichi, Tachikawa. Japan had aircraft manufacturers with tens of thousands of workers and decades of experience. The problem was not that Japan lacked places to build airplanes. The problem was how those places worked. In Japan, a skilled worker made a part. He filed it, measured it, adjusted it. If it did not fit, he filed it again. The part fit because the man who made it was good at his job. If that man got sick, or was drafted, or was killed in an air raid, the next man filed differently. The next part fit differently. Quality depended on individual hands, individual eyes, individual years of experience. The system was the craftsman. Remove the craftsman, and the system broke. At Boeing's Wichita plant, the system was the opposite. The workers who built B-29s in 1944 were not, for the most part, aircraft engineers. Many had never seen an airplane up close before they were hired. 40% of the workforce at the Bell plant in Marietta, Georgia, were women. Riveters, welders, sheet metal fabricators, crane operators. They had been secretaries, waitresses, school teachers 6 months earlier. They built Superfortresses at a rate of 2 per day, not because they were more skilled than the craftsmen at Mitsubishi, but because the system did not require skill of that kind. The tolerances were in the tooling. The precision was in the jigs, the fixtures, the dies, the templates, standardized, calibrated, identical from one station to the next. A worker did not need to know why a rivet went in a particular location at a particular depth. The jig told her where. The pneumatic gun told her how deep. The inspector at the next station told her if she had done it right. The knowledge lived in the process, not in the person. This is what the rivets on that B-29 skin panel were actually saying, not that American workers were better. That American workers did not need to be better. The system had removed the human variable, and a system that does not depend on irreplaceable individuals can do something that a craft-based industry cannot. It can scale. The Tachikawa engineers understood manufacturing. They understood what they were seeing, and what they were seeing was a mirror held up to every weakness in Japan's industrial base. Consider the wiring. 10 miles of electrical cable inside every B-29. Not custom-cut, hand-soldered wiring bundles. Prefabricated harnesses, built to specification at subcontractor plants, shipped to the assembly factory, and plugged in. The B-29 program involved thousands of subcontractors spread across the United States. Chrysler built engine components. Fisher Body built fuselage sections. Goodyear made parts. Hudson Motor contributed assemblies. These were automobile companies, appliance manufacturers, firms that had never built aircraft parts before 1942. By 1944, they were producing them to aircraft tolerances, by the thousands, on schedule, interchangeable from one B-29 to the next. Japan's subcontractor network was the opposite. Mitsubishi's Nagoya works relied on a web of small workshops scattered across the city. Family operations, 3 or 4 men with hand tools, producing parts that often needed to be reworked at the main plant before they could be installed. When the B-29 firebombing campaign began in March 1945, it was not the main factories that collapsed first. It was the subcontractors, the small shops, the networks, the little buildings made of wood, scattered through residential neighborhoods that burned. And when they burned, the supply of parts stopped, and the main factories, still standing, still staffed, had nothing to assemble. The Americans had, without knowing it, designed a bombing campaign that attacked the exact vulnerability that made Japanese aircraft production fragile. Not the factories, the system. But here is the layer beneath that layer, the one that made the Tachikawa engineers go quiet. The B-29 production system was not built for the B-29. It was a general-purpose capability. The same tooling philosophy, the same subcontractor networks, the same workforce training methods that produced Superfortresses also produced Mustangs, Hellcats, Corsairs, Liberators, Shermans, trucks, jeeps, radios, artillery pieces, and ships. Thousands of ships. The system was not a response to the B-29. The B-29 was a product of the system, and that system could build anything, faster than Japan could build its one equivalent. In 1944, American factories produced more aircraft than Japan built in the entire war. That sentence sounds like an exaggeration. It is not. The United States produced just under 100,000 military aircraft in 1944 alone. Japan produced approximately 28,000 across all 6 years of its war, from 1939 to 1945. America built more in 12 months than Japan built in 72. The engineers at Tachikawa did not have access to these figures, but they did not need them. They had the wreckage. And in the wreckage, every rivet, every wire, every seal, every computer told the same story. A story not about a better airplane, but about a civilization that had learned to turn raw materials into precision machines on a scale that Japan could not match, could not approach, and could not survive. And yet, there was still one more thing inside that wreckage. One component they had not yet fully examined. Something that revealed not just the depth of the gap, but its direction. Where America was going, and how far behind Japan already was before the first B-29 ever left the ground. The component was the fire control computer itself. Not what it did, the engineers already understood that, but how it was built. When the electrical specialists at Tachikawa pried open the steel casing and began disassembling the General Electric analog computer, they were not looking at gears. They were looking at relays, small, electrically driven mechanical switches that opened and closed in sequences determined by the input signals from the gun sight. Hundreds of them, wired in precise configurations, each one performing a single logical operation. Together, they calculated ballistic solutions faster than any human gunner could think. The computer did not approximate. It solved differential equations in real time, at altitude, in turbulence, while the aircraft shuddered from its own engines and the concussion of flak bursts. But here is what stopped the engineers. The relays were identical, not similar, identical. Mass-produced to tolerances so fine that any relay in the box could be swapped with any other relay in any other box in any other B-29, and the computer would function exactly the same way. These were not hand-wound laboratory instruments. They were factory components, stamped, assembled, tested, and shipped like ammunition. General Electric had manufactured nearly 4,000 complete fire control systems by the end of the war. 20,000 individual computers, hundreds of thousands of relays, each one interchangeable. Japan in 1944 was still building aircraft instruments largely by hand. A gun sight was assembled by a technician who adjusted each unit individually. If the unit broke in the field, it could not simply be replaced by another unit from a crate. It had to be repaired by a trained specialist with tools in conditions that combat rarely provided. The American system assumed that things would break. It was designed so that when they broke, a 20-year-old mechanic with a manual could pull the dead unit, bolt in a new one, and have the aircraft combat-ready in hours. The Japanese system assumed that things would work. When they didn't, the aircraft sat. And this is where the fire control computer stopped being a weapon and became a prophecy. The engineers at Tachikawa were aircraft men. They understood engines, airframes, propellers, guns. But the device in front of them was not an aircraft component in any traditional sense. It was an electronic brain. It took information from the physical world, the speed of the wind, the angle of the target, the temperature of the air, and it translated that information into mechanical action without human intervention. The gunner pointed, the computer aimed, the guns fired where the target would be, not where it was. This was not an improvement on existing technology. It was a departure from it. Japan's entire approach to aerial gunnery, Every fighter, every bomber, every defensive position depended on the skill of the man behind the trigger. Train him long enough, give him enough flight hours, and he becomes deadly. The Americans had taken the man out of the equation. They had built a machine that turned an average gunner into an expert, and an expert into something that did not miss. Consider what this meant for the Japanese pilots who were ordered to intercept B-29 formations. By the winter of 1944, Japan's interceptor force was already crippled. Fuel shortages had cut training hours so drastically that new pilots arrived at their units with fewer than 100 hours of total flight time, a fraction of what their predecessors had in 1941. Experienced pilots were dead or exhausted. The aircraft available to intercept B-29s were a patchwork. Ki-45 heavy fighters, Ki-61 singles, a handful of the newer Ki-84s, some modified reconnaissance planes with upward-firing cannon bolted into the fuselage. Most could barely reach the altitudes where B-29s cruised. Those that could arrived gasping at their service ceiling, sluggish, barely maneuverable, their pilots lightheaded from cold and thin air. And waiting for them was a defensive system that tracked them from the moment they entered range, calculated their trajectory, and concentrated the fire of multiple turrets on a single aircraft with a precision no human crew could match. The official post-war report credited B-29 gunners with 914 aerial victories against 72 B-29 losses in combat, a kill ratio of nearly 13-to-1. That ratio was not the product of superior marksmanship. It was the product of 5 50-pound boxes that thought faster than the men attacking them. The Japanese military's response to this problem tells you everything about how wide the gap had become. Unable to match the B-29's altitude, unable to penetrate its defensive fire with conventional attacks, Japanese commanders turned to the one tactic that no computer could calculate against: ramming. Corporal Matsumi Nakano, the pilot whose kill had delivered the wreckage to Tachikawa, had not shot down his B-29. He had flown his Ki-61 directly into it. He survived, belly-landed his shattered fighter, and was celebrated as a hero. 2 months later, on January 27, 1945, he did it again, rammed a second B-29, and survived a second belly landing. He was one of the lucky ones. Most pilots who attempted ramming attacks did not survive. The tactic was formalized. Special ramming units were organized. Shinton squadrons, stripped-down fighters with reinforced wings and reduced armament, designed for a single purpose. The pilots volunteered. They knew the mathematics. Against an aircraft defended by 5 interconnected computers, the most effective weapon Japan could deploy was a man willing to die. Think about that. Hold it in your mind. Because this is the moment where the story of what the engineers found in the wreckage and the story of what was happening in the sky above them become the same story. The engineers disassembled a computer that made human skill irrelevant. The pilots flew into aircraft defended by that computer, with nothing but velocity and willpower. Both groups, the engineers in the hangar and the pilots in the sky, were looking at the same truth from different angles, and both groups arrived at the same conclusion. But it was the engineers who wrote it down. The reports that circulated through Japan's aviation establishment in the first months of 1945 did not read like military documents. They read like autopsies. The language was technical, the conclusions were precise, but beneath the engineering terminology, the men who wrote those reports were describing something that transcended airplanes. They had examined the B-29 component by component, the alloys, the wiring, the pressurization seals, the turbochargers, the fire control computers, and each component had told the same story. Not a story about one aircraft that was better than anything Japan could build. A story about a country that could mass-produce things Japan could not hand-build. And there is a difference between those two sentences that changes everything. If the Americans had built one extraordinary B-29, a prototype, a showcase, a proof of concept, it would have been alarming but not fatal. Japan knew how to build prototypes. The Renzen was a prototype. It flew. It worked, mostly. The gap between a single American marvel and a single Japanese achievement was real, but not unbridgeable. Engineers solve problems. Given time, given resources, given materials, Japan could have narrowed that gap. But the B-29 was not a prototype. It was a production item, and the wreckage at Tachikawa proved it, because the parts inside were not hand-fitted. They were not individually adjusted. They bore manufacturing marks, lot numbers, inspection stamps from factories scattered across a continent. The aluminum came from one place, the wiring harnesses from another, the computers from another, the turbochargers from another. Thousands of companies, hundreds of thousands of workers, a transcontinental supply chain, all converging on 4 assembly plants that bolted these components together at a rate that increased every month. The engineers understood what this meant. Japan could not close the gap because the gap was not technological. It was systemic. To match the B-29, Japan did not need a better airplane. It needed a better country. Better metallurgy, better electronics, better machine tools, better raw materials, better roads, better trains, better subcontractors, better education, better everything, all at once, all immediately. And it needed them while its cities burned, its shipping lanes were severed, its oil reserves were gone, and its aluminum production was falling toward zero. The Tachikawa Report was not the only document that reached this conclusion. Throughout the spring of 1945, as B-29 raids escalated from dozens to hundreds of aircraft per mission, Japanese military and civilian leaders were arriving at the same understanding through different paths. On the night of March 9, 1945, 334 B-29s flew over Tokyo at altitudes so low, 5,000 to 9,000 feet, that the fire control computers were almost unnecessary. General Curtis LeMay had stripped the bombers of most defensive armament, removed the gunners, loaded the weight savings with incendiary bombs, and sent them in at night, in a stream, over a city built of wood and paper. The Pathfinder aircraft marked the target zone with napalm. The main force followed. The resulting firestorm killed an estimated 100,000 people in a single night and destroyed 16 square miles of the capital. 267,000 buildings ceased to exist. 1 million people were homeless by dawn, and the raid had cost the Americans 14 aircraft, 14 out of 334, a loss rate of 4%, replaceable in a single day of production at Wichita. That ratio, a city destroyed, 14 aircraft lost, all replaceable by sundown, was the B-29 story reduced to its purest form. It was not about the airplane. It was about the fact that America could lose B-29s faster than Japan trajectory. You can see the end from the beginning. By the summer of 1945, Japan's aircraft engine testing had collapsed. New engines that once received 7 to 9 hours of bench testing before installation were now, and without those parts, the main factories assembled aircraft that did not work. Japan produced approximately 28,000 military aircraft across the entire war, a formidable number in isolation, but place it next to the American figure, nearly 100,000 aircraft in 1944 alone, and the number becomes something else. It becomes the answer to the question the engineers had been circling since December. The question was never whether Japan could build them at the time, something so small they almost didn't record it. It was only years later, long after the war, that its meaning became clear. Among the components recovered from the wreckage, the Tachikawa engineers found a small metal plate riveted to the airframe near the forward bomb bay. It carried a string of numbers and letters, a data plate, serial number, production block, manufacturer code, date of manufacture, standard markings, found on every military aircraft in every air force in the world. The engineers recorded the information and moved on. There was nothing remarkable about a data plate. Every aircraft carries one. But the date on that plate was remarkable, though they had no way of knowing it at the time. Because the B-29 that Corporal Nakano had rammed out of the sky on December 3, 1944, serial number 42-24735, had been ordered in 1942. The 42 in the serial number was the fiscal year of the contract. The aircraft had gone from a purchase order to a flying, pressurized, computer-defended, turbocharged bomber in roughly 2 years. 2 years, from contract to combat over Tokyo. In those same 2 years, Nakajima had not yet completed the first prototype of the Renzen. That data plate, a small rectangle of stamped aluminum that the engineers cataloged and filed, contained the entire war in miniature. Not the war of battles and islands and naval engagements. The war underneath. The war of how fast a nation can turn an idea into a machine, and a machine into 1,000 machines, and 1,000 machines into a force that darkens the sky over another nation's capital. Japan lost that war before the first B-29 ever took off. The engineers at Tachikawa were simply the first to read the evidence. After the war, the occupation authorities interviewed Japanese military and industrial leaders for the United States Strategic Bombing Survey. The interrogations covered every aspect of the conflict: strategy, production, morale, the decision to surrender. Among the thousands of pages of testimony, a pattern emerged. When asked about the B-29, Japanese officials, officers, engineers, factory managers, cabinet ministers, did not talk about the bombs it carried. They did not talk about the firestorms. They talked about what the aircraft represented. They called it the single most important factor in convincing them the war could not be won. Not the atomic bomb, not the Soviet declaration of war, not the loss of Okinawa, the B-29. Because the B-29 was not a weapon, it was proof. Proof that the enemy could reach you, that the enemy could not be stopped, that the enemy could replace its losses faster than you could inflict them, and that behind every aircraft you shot down there were 10 more, built by people who had never built airplanes before, in factories that had made cars a year ago, using a system so powerful that it did not even need experts. The wreckage at Tachikawa told this story one component at a time. The rivet that was too perfect, the alloy that could not be sourced, the turbocharger that could not be built, the computer that could not be imagined, the production rate that could not be believed. Each piece was a word. Together they formed a sentence. You are not behind. You are somewhere else entirely. Corporal Matsumi Nakano survived the war. He had rammed 2 B-29s and walked away from both crashes. The wreckage of his first kill went to Tachikawa, where it taught Japan's best engineers that the war was already over. A mock-up built from its remains went to Hibiya Park, where crowds gathered to stare at the monster that burned their cities every night. The aircraft was presented as a trophy. The engineers knew it was a verdict. The Tachikawa Army Aviation Technical Research Institute was seized by American occupation forces in September 1945. The reports were confiscated. The engineers went home, to cities that were ash, to families that had survived or had not, to an industry that no longer existed. Japan was forbidden from building aircraft for 7 years. When the ban was lifted in 1952, some of those same engineers returned to aviation. They brought with them the memory of a 50-pound metal box that aimed guns by mathematics, of an aluminum alloy they could measure but could not make, of 4 factories producing 100 bombers a month with workers who had been civilians the year before. They did not try to build a B-29. They did something the B-29 had taught them was more important. They built the system. They studied American manufacturing methods, American quality control, American standardization. They learned to make things not by hand, but by process, not one at a time, but by the thousand, not through craftsmanship alone, but through systems that did not depend on any single craftsman. The engineers who opened a B-29 and saw the end of their war spent the rest of their lives building the beginning of something else. The lesson of the wreckage was not that Japan had lost. The lesson was why. And once they understood why, they made sure it would never be true again. Thank you for staying with this story all the way to the end. If it meant something to you, a like genuinely helps. It tells the algorithm that this kind of history matters, and it helps these videos find the people who care about them. If you're not subscribed yet, I'd be honored to have you. Hit subscribe and tap the bell so you never miss a new one. I'd love to know, where are you watching from today? And if someone in your family served in the Second World War, in any theater, on any side, tell us about them in the comments. Every one of those stories deserves to be remembered.